Okay, guess we can move on. Before we do the geology, I have one final little bit of mathematics to throw at you. It's pretty simple. And this is something we're going to use a little later in the semester as well. What I'm trying to do today is give you a few tools that we're going to apply over the final month of the semester when we start talking about how wells really work. Okay, so one of the quantities that is sometimes useful to know is how much pressure, how much water pressure exists at the base of a well. So in this case, we're drilling a well into a confined aquifer. The water's under pressure, and the water rises up to a certain level in the well because of that pressure. Well, how much pressure is at the base of the well to make the water rise? So what I have right here is an equation from a couple weeks ago. It says the total head, the total height of the water column, equals an elevation head. And remember, the elevation head is the distance from sea level to the base of the well. Okay, it may be a few feet, a few hundred feet. Around here, it'll be probably a few thousand feet. Okay, that's the elevation head. And then there's also a pressure head, and that is the height that the water rises from the base of the well into the well at some level. Okay, so it's the height that the water rises in the well. That's the pressure head. Now, what I'm asking in this is to calculate the pressure at the base of the well. So what is the water pressure right here at the base of the well that forces water to move up to that level right there? So what we're really going to focus on then is this pressure head right here. So in this particular case, let's just put some numbers on it. Let's say that pressure head was 70 meters. Okay, so the water rose up 70 feet in the well. So how much pressure was required to make the water rise that high? Well, it's actually pretty easy to calculate. It comes from an equation we had earlier where the hydrostatic pressure equals the height of the water column, or in this case, the pressure head, times gravity times density of water. What's our pressure head in meters? In this case, it's 70 meters. What's the acceleration due to gravity? 9.8 meters per second squared. Density of water. I gave you a couple values earlier semester. 1 gram per cubic centimeter. Also 1,000 kilograms per cubic meter. If you remember that one, you don't have to do any conversions. If you multiply those things together, you get 6.86 times 10 to the 5th pascals. That's the pressure at the base of the well. The height of the column of the water, the pressure head, times gravity, times density. All in the same units. So it's helpful to remember the density of water per cubic meter for these types of calculations. It's 1,000 kilograms per cubic meter. So 70 times 9.8 times 1,000, 6.86 times 10 to the 5th pascals. Okay? We're not going to do much more with that today. We'll come back to it in a few weeks. I just wanted you to see it once before we see it again in a couple of weeks, okay? So you can look at it. You'll forget it. We'll come back to it. Always seems like people remember things much better the second time they see it. So I like to throw things out multiple times for you. Do you have any questions on how this is calculated? Okay, let's do some geology. All right, we're going to talk about groundwater flow over the next few weeks and talk about pumping wells and how that will affect the flow of groundwater in an area. And one of the primary things that determines how groundwater flow is how porous and permeable your rocks are. Okay, so we're going to spend a little bit of time doing something that's not normally done in a lot of groundwater classes. Usually groundwater classes are all about the math, but I'm a geologist, and out in the real world, you can't ignore the geology. So to understand that something about the rocks you're dealing with is always going to help you make decisions about how things are really working out in nature. So we're going to talk about where does porosity and permeability come from in different kinds of rocks. So porosity and permeability are a function of several things out in the geologic world. It's a function of the rock itself, how it was formed, and any alterations that happened to it since it's been formed. For example, a granite and a sandstone, they form totally differently, right? Granite forms from the solidification of magma. A sandstone forms in a beach or a river in a dune environment where little sand grains are cemented together. Those are really different processes, right? And they result in rocks that have very different kinds of porosity. So how it forms affects the porosity. But after the rock is formed, a lot of things can happen to it, right? It can be broken by tectonics. It can experience weathering. We talk about weathering in a lot of our geology classes as well. Weathering can affect the porosity. So that's what I'm talking about when I say alterations that the rock has experienced. So we can really think about this maybe in two different ways. We have what's called primary porosity. This is kind of the porosity the rock was born with. Pores that form when the rock was formed. Don't know what happened to it. I lost it. Oh, it is. Hang on a sec. Do it this way. I'll get my notes back here somewhere. All right, that should be really, really nice. Technology. Hey, that worked. Pores that form when the rock forms. And then we have what's called secondary porosity. Pores that form after the rock forms. Primarily through tectonics and weathering. So what I'd like to do is kind of go into each rock type, talk about how pores might form when the rock's forming, what might happen to it afterwards. In a couple weeks, I'm going to give you an exercise with a geologic map. You're going to look at the rock units in an area, try to figure out which ones might be porous and permeable, which ones would make the best aquifers, which ones would probably be confining layers, and then take a look at how deep those rocks might exist beneath the surface and get some idea of how deep you would have to drill to find water that would be able to make a well function properly. Okay, so I'm going to try to give you some real world exercises here over the next couple of weeks. I'm going to give you one here in a little bit that's going to be due in a couple weeks. And then we'll do another one with geologic maps in a couple weeks that'll be due later in the semester. So we're going to have sort of two big assignments coming up where you're going to use real maps and hopefully a problem that sort of mimics what you might encounter out in the real world. Okay, so let's start with the major rock types. Let's start with igneous rocks. What are igneous rocks? Going back to your physical or introductory geology class. Give me your definition of an igneous rock. Rocks formed by the cooling of magma, okay? And that cooling can take place on the Earth's surface with a volcanic rock or inside the Earth with an intrusive rock, right? Okay? So think about that for a minute. What sort of, if any, primary porosity is going to exist in an igneous rock? A pore that's going to form when the rock forms. Okay, so in the Earth, right, it's under a lot of pressure, right? So you have melted rock. As it cools off, those crystals grow and they sort of interlock together, right? So for intrusive igneous rocks, like granite, gabbros, diorites, all those crazy intrusive rocks that if you haven't had petrology, you'll learn about in petrology or you'll see in a petrology book somewhere. Basically, you have very little primary porosity. Dense, no holes in it. What about volcanics? Can you get some pores in volcanics? What's the origin of the pores in volcanics? Yeah, for volcanic rocks, there's really sort of two origins. One you just mentioned are gas bubbles. Typically, just a few percent. And importantly, many of these bubbles do not connect. You have a bubble here, and you have a bubble here, and you have a bubble here, and another one here, and they don't connect. So even though there might be some pores, it's not going to be permeable at all. Now that's for most lavas. We do have eruptions on Earth that are explosive, that can create deposits of ash. That's almost like a sedimentary rock in a way, where you have ash particles that land on other ash particles, and there can be pore spaces between the ash particles. So for ash deposits, We sometimes call these volcanic tuffs. Tuffs are rocks that are made of ash. Pores exist between ash particles. We do have things that are called welded tuffs. These are where the ash, this is where the ash is so hot that it sort of refuses itself back together. And when that happens, a lot of the space between the ash is eliminated. So it becomes a very dense rock again. So for welded tuffs, you get very little porosity. So the bottom line is that, for the most part, volcanic rocks don't have much for primary porosity. The only real exception would be a pumice, right? Pumice fragments are like 70% pores. But even in pumices, the pores aren't connected. So the water or any other fluid that you might have trying to move through it can't really do it. So with igneous rocks, we have very little effective primary porosity. For intrusive rocks, there just isn't much. Rare odd gas bubble. For volcanic rocks, you can get a few percent gas bubbles in lava flows, and you can get a fair bit of porosity in ash deposits, unless the ash welds back together and reduces the porosity. So there's not many volcanic rocks that are very porous to start with. They can be modified after by tectonic forces or weathering, but just as they form in nature, there's not a whole lot of porosity going on here. All right, another class of rocks are the metamorphic rocks. What's a metamorphic rock?
Rock formed by extreme pressure caused by aerial.
Okay, so it's a rock that's altered in the presence of heat, pressure, and sometimes fluids. Okay, so you have a parent rock, and a parent rock could be just about anything out there. And then it experiences heat and pressure and fluids. Okay? Do you remember the different types of metamorphism? There are two primary classes of metamorphic rocks. You guys remember what those two were? If you don't, that's okay. We have what's called contact metamorphism. In this case, your parent rock, whatever is being metamorphosed, is heated by a nearby magma body. But doesn't melt. Instead, what happens are the crystals in the parent rock grow as the heat sort of rearranges some of the atoms. When those crystals grow, it tends to reduce the porosity. An example would be you could start with, say, a sandstone that has maybe 30% pores, really porous sandstone. And if a magma body comes up close to it and bakes it, those sand grains will start to rearrange their structure a little bit because of the heat. The heat breaks a few bonds and it's able to make some of the atoms in the sand grains rearrange, and they start to grow a little bit. And you end up with a rock called a quartzite, which is a really dense rock that has almost no pores at all. So contact metamorphism can reduce the porosity by baking and recrystallizing these grains. We also have a type of metamorphism called regional metamorphism. I might as well put this with the contact. There's a couple of common contact metamorphic rocks that you should know of. One is called marble, which is a recrystallized limestone. And the other is called a quartzite, which is a recrystallized sandstone. So in both cases, marble and quartzite tend to have less porosity than their parent rocks, which are limestones and sandstones. They get baked. They just get baked next to this magma, and that causes reorganization of the little grains that reduces porosity. So regional metamorphism, and if you've had a class, talks about low grade, where you get slates and phyllites, up to high grade, which are schist and ultimately gneiss. And this results from stress, pressure, heat, and fluids in a plate tectonic environment. So plate boundaries are areas where you have lots of heat, lots of pressure, and lots of fluids moving through. And because of the extreme pressure from plates colliding, these rocks tend to what we call develop a foliation. A foliation is a preferred alignment of grains. Usually it's in the micas. It makes the micas lie flat. If you've seen slate, like the blackboard up here, these are actually lots of tiny grains that are lying flat. Crank up the heat and pressure a little bit, and the grains grow a little more, and you start to see a shine on it. That's a phyllite. Crank up the heat and pressure a little more, those grains get even bigger, now to the point where you can see it, and you get a schist. And if you guys have seen schist before, you know it's got lots of mica in it. And the mica are all pressed down sort of flat on one another. And then if you crank the heat and pressure up even more, you get a gneiss, where you get bands of light and dark minerals. So you get a preferred alignment or foliation of minerals. The grain size tends to grow with increasing metamorphic grade, which reduces porosity. Grain shape tends to change. They tend to get bigger and flatter until you hit the gneiss stage, and then you get new minerals form. So grain shape tends to change as well. The result is that you get lower porosity at higher grades of metamorphism. And because of the preferred alignment of grains, water doesn't flow the same way equally in the rock. Let's say you have mica grains that are all lying flat, okay? water can move between the grains pretty easy. It can't move across the grains very well at all. So that is what we sometimes called, I got to rewrite this because for some reason this is not working, an isotropic flow. Basically, water flows at different speeds in different directions because of the preferred alignment of grains. Bottom line for metamorphic rocks is that the porosity is complicated. You've got grains growing, you've got grains changing shape, you've got grains that are getting pressed together in preferred alignments. And that makes trying to figure out the porosity and permeability really difficult. So if you really want a complicated rock to do groundwater with, find yourself some metamorphic rocks. Make yourself really miserable. Now, in some areas, that's all you have. Luckily, in most areas, you also have other kinds of rocks. So the rocks we tend to deal with the most in groundwater geology are the sedimentary rocks. And there's a reason for that. First and foremost, it's the most common class of rock found on the continents where we live. So this is the rock just by odds you're most likely to deal with. The other thing, these are rocks we look for because primary porosity tends to be much higher than with igneous and metamorphic rocks. And for our purposes, it's important to note that the porosity had it. I don't know how I get it back. I gotta do this again, seriously. Technology. All right. The porosity is highly affected by how the rock forms. For example, porosity is going to be affected by the grain shape. And when we talk about grain shape, we typically talk about grains being rounded or angular in something like a sandstone. Grain shape reflects transport distance in the sedimentary environment. The farther something is transported, the more round the grains tend to be. Grain size actually affects porosity quite a bit as well. Grain size reflects the energy of the transporting medium that brought the sediment to its final resting place. So gravel requires a much more powerful transporting medium than silt and clay. And then one thing that really affects porosity a lot is something we call sorting. I'm guessing you've heard of sorting in one of your previous geology classes. If you don't remember, and most geology students seem to have issues with sorting. It's really not a difficult concept. It's the consistency of particle size in a rock. So sorting, we can have something that's called well sorted, where most of the grains are the same size. Or we can have a rock that's what we call poorly sorted, where the grains in the sedimentary rock are different sizes. And this is the one thing that's probably worth remembering from this little section is that well-sorted rocks tend to be more porous. Because let's say you had a bunch of nice rounded sand grains that are all the same size, like I'm drawing right here. I'm drawing really poorly right here, okay? So there's my lousy sandstone right there. But if you look, you'll have to imagine because my drawing is so poor, but you can imagine that there's lots of pore space between the sand grains, right? Now, if you have a poorly sorted rock where you can have a lot of small fragments in there, sometimes those small fragments can fill in the pores. So if you have a poorly sorted rock with lots of clay and silt, it can get in between the sand grains and sort of clog up the pores. And you don't get as porous of a rock. So well-sorted rocks tend to be more porous than poorly sorted rocks. All right, we're going to finish with one little bit, a definition of porosity. I've been talking about porosity, but haven't really defined it yet. So let's just give a simple definition for porosity. It's really easy. It's the portion of rock comprised of pore space. And it's typically expressed as a fraction when we do groundwater work. Sometimes as a percentage as well. Mathematically, it's really simple. Pore space, which we usually give an N to in groundwater, not again. Okay. Every week I have a new challenge to deal with technology in this class, it seems. Okay, so pore space, N, is the volume of voids, open space. Divided by the total volume of rock. Which also includes the voids. I'll give you an example, hopefully, to illustrate this. So if our volume of voids, let's say we have a total volume of a cubic meter. Let's say we have a cubic meter of rock, okay? So we have a rock, a sandstone. It's a meter on a side, okay? A big cube of sandstone. And 0.026 of that rock is voids. 0.026 divided by 1 equals 0.026 or 26%. Let's say I gave you a sandstone. Let's say I gave you a sandstone that's about the size of my head. Okay, I just hand you sandstone. In fact, we probably have some over here along the wall. Say I gave you one of those rocks. How would you figure out the porosity? Can you think of a way to figure out the porosity of one of those rocks? How much pore space is in there?
Submerge the rock in water.
Okay.
For like an hour, take the rock out real quick and see how much water was absorbed.
Okay, so let's say you have your rock. You can measure the volume of the rock by, you can put it in water and see how much water is displaced. That gives you the volume of the rock, right? And then, like you said, over the next hour, let that water soak into the rock. All right? And once you feel that the rock is totally saturated, you pull the rock out. See how much water is missing, right? The amount of water that's missing is the amount that's in the pore space. That gives you a pretty good estimate. Will give you a perfect estimate. In order for the water to get in, what has to happen with the pores? They all have to be connected, right? What if you have some pores that aren't connected? Then there's no way for water to get in there. But as it turns out with groundwater geology, we don't care so much about the unconnected pores. We talk about things called effective porosity, just the pores that are connected. That's what really matters. That's what allows water to flow through. So that's what we're going to try to get at is what is the effective porosity of the rock? Just how much of that rock can water make its way into? So over the next few weeks, that's what we're going to deal with, is something called effective porosity. So you saturate your rock, you look at the loss of water. You can do that by weighing the rock or measuring the water there ahead of time. There's a lot of ways you could practically do it. But scientists actually spend time with different types of rocks, sedimentary rocks, igneous rocks, metamorphic rocks, figuring out the porosity so that you don't have to. You know, if you want to know, okay, what's the porosity of sandstone? You can try to measure it yourself, which is a real pain. Or you can just go to a book where these scientists have measured lots of different sandstones, and they'll give you a range of porosity. Sandstones range between 21 and 28%. So you pick the value that you think best represents your rock and you use it. So a lot of the work is done for you ahead of time. All right, you guys seem saturated tonight. So any questions? All right, I have an assignment up here for you somewhere. You can come pick it up. It's due in 2 weeks for the people online. It's also due in 2 weeks. I'll put the assignment on the website. It's pretty simple. Everything you need is right in there. I have maps and everything for you to draw on. And it's pretty self-explanatory. But if you need help, email me and I'll be happy to email back or set up a Zoom meeting, whatever it takes to help you get through it. I think I have it worth 10 of your homework points, so it's a pretty significant part of your homework grade. We're going to have 2 more homework assignments, this one and the next one. They're both going to be probably worth a letter grade by the end of the semester, so take them serious. You've got a couple weeks. Don't wait till the last minute because this one does take a little